Thank you very much for arriving to us today. My name is Andrea Puruc and I work for Pannon Business Network Association. I am the organizer of today's training, and I am the consortial partner of the SMERF Central Europe project. In the coming minutes, I would like to give you a short overview about the frame of this event, what are we working in with my partners, and after this we are going to listen to the presentation of two of my engineer colleagues in the very specialized topics you will see. The agenda of today's event is very, very simple. So we will have the presentations, and as you wish, you can, if you have any questions, you can also raise your hands, or if you want, you can also write questions into the chat section. And after the presentations, there will be also the room for asking asking information from our expert colleagues. Okay, let me share with you my presentation. And I will ask one of my colleagues if you can give me a bit feedback that you can see my presentation and you can see also changing the slides.
Yes.
Yes, great. Thank you very much. Yes. So as I mentioned, my name is Andrea and work for PBN Hungary. And today's event is the digital manufacturing training. This training is part of a set of trainings organized in the SMERF project. It's, if I remember well, this is the 5th training, and we will have also some for the near future in the organization of our kind partners. So what is the SMERF project? I don't want to bother you with a lot of information, but only a few things. You can see our kind team here in the photo. We are 8 project partners in the Central Europe region, and the main mission of our activity is that we would like to support mainly low-tech and medium-tech small and medium-sized enterprises, helping them in the transition towards SME ready for future, because SMERF is the abbreviation of SMEs ready for future. So the main thing is supporting SMEs in transition. Then the other very important focus is to provide new services to higher education institutions and the intermediaries, so those kind of actors who are supporting the SMEs or who are closely working together with them. Here you can see the partner list. It is also interesting for you if you want to contact one of our partners for further cooperations. You can contact in Wrocław University, Business Upper Austria, Center of Research and Technology, in Italy, Karlsruhe Institute of Technology, Pannon Business Network, STEPRI in Croatia, University of Genova, and Technical University in Košice in Slovakia. So we are working together. And what is our main motivation? This is not a rocket science, and you already know that small and medium-sized enterprises are struggling really high challenges. For example, SMEs face the need to effectively transition and adopt new market and social-driven concepts, and they don't have sufficient capacities to do this. They have difficulties in digitalization and innovation, and of course also in internationalization, and we can state that all in the Central Europe regions, this is the situation also today. There is also very typical that innovation level is very low inside the SMEs. You can see some data also here. And also the low level of cooperation and knowledge transfer between SMEs, different actors of the region, universities, business support organizations, and research centers. So we have to support this. And what is also important that we are focusing on more levels, on more topics, because all these 4 topics are really connected together. Innovation culture, digital manufacturing, open innovation and sharing economy, and the green and circular economy and sustainability. These are the 4 pillars along which we are working in our activities and trying to support SMEs. And we also have services and results which have been already achieved, and these are the following, and you can also capitalize from them. We have a so-called inspirational knowledge base. You can see the link here. If you go there, you can, after registration, this is free of charge, only registration required. You can read about SME good practices, describing successful transition stories, and you can also watch trainings in these kind of topics and webinars in the 4 main topics highlighted before. Then, which is one of our main results, is that we elaborated the so-called SMERF diagnosis tool. This is already also available and full functioning. You can reach it on this link below. And this is a free of charge online analysis tool for small and medium-sized enterprises. Also in the 4 topics which were presented to you, the main feature of this tool is that after completing very short and focused questions in the 4 topics, the SME can receive feedback on weaknesses and very good features they reach, and on the same time, based on these audit results, the system provides for the SMEs individual transformation scenarios. How can you make the second step, the next step to it? And also you can contact our network, our consortium, and in this consortium we have experts who are specialized and can provide services to SMEs to reach somehow these scenarios. And this tool is already tested with the participation of 160 SMEs who helped us really to really fine-tune it to the SMEs' needs. And then, as I mentioned, we have experts and mentors who are helping in our SMERF individual support program to support the SMEs on their individual needs to develop. And yes, sorry, I mentioned this twice, but the main thing is that we also have the mentors, dedicated expert team. And it is also very important because it was a very nice event, and later on we can help you to find these kind of events as well. That we had the so-called Green Market. This was this time organized in Austria. It was a cross-regional event for learning and networking. So this helps also SMEs to achieve goals like internationalization and learning from experts in different topics. This event's topic was, for example, AI from different perspectives. And I don't want to speak more about projects because we are here rather for very detailed information. Let me introduce my 2 colleagues, Dr. Ferenc Tollner and Boldizsár Könsel. They are working in Pannon Business Network, but exactly in the digital innovation hub of Pannon Business Network, responsible for Industry 4.0, digitalization and AI technologies, supporting SMEs on a daily basis through different services. So first of all, I would like to ask Ferenc to present the first material of our training. And after this, Boldizsár will continue. So thank you. I will now stop sharing my screen and hand it over to you, Ferenc.
Okay, I would like to greet everybody. My name is Ferenc Tollner, and I also, as Andrea did, I would like to ask for a kind feedback from you that you see my presentation and I'm audible.
Yes, I can hear you and see your first slide.
Okay, thank you very much. So this presentation will be about implementation of AI-related solutions in a Hungarian company. I will briefly speak about the problem setup and the project goals that were targeted, about the range of available historic data and ML machine learning techniques that were used within this project. about some real-time dimension measurement tools that were mounted within the production area, about the results and concerns, and some further extension possibilities of such and similar kind of AI-related investigations. So what we did, we were involved in a project that had the aim to investigate production-related information in case of so-called pull Trojan processes. What is pull Trojan? Pull Trojan is a kind of plastic production process where a continuous fiber reinforced plastic is produced. Pull Trojan, the word means is technically the abbreviation or the addition of two English words, pull and extrusion. In this process, fibers or woven or braided strands are impregnated with a resin, and this is possibly followed by a separate preforming system and pulled through a heated polymerization, heated stationary die where the resin undergoes polymerization. Here, different kind of resins can be used, like polyester, polyurethane, vinyl ester, or epoxy, etc. These are the main ones. And this resin provides resistance against the environment, like corrosion, UV, or impacts. And within the plastic inside, there is a glass fiber that gives sufficient strength in addition to safety from fire. Here is an image how such a pull Trojan production line shall be imagined. In the back, there are the huge drawings of glass fibers that are guided and pulled through curing die, and afterwards the fibers that are covered with this resin are solidified and cut into specified lengths, and that will give the final product. Some images out of such a system or company. On the left, you can see how simple the initial stage of the inlet of these fibers are, which are undergoing in this resin tank. And in the right bottom corner, you can see some profiles through which these resin-covered fibers are pulled through, and this is technically the pull Trojan process where it happens. You pull out this plastic-covered fiberglass, and you apply some heat according to a specified heat profile, and the resin will cure and solidify on the fiberglass in a specific shape. Some produced goods that can be achieved via such a process, mainly long tubes with different profiles that can be used in windows or other structural areas. The main point of such technology applications that you can achieve plastics that are extremely strong compared to other plastics. So they are technically now compatible with iron and steel. Of course, there are other advantages as well, like corrosion resistance, UV resistance, abrasion resistance. Also, it should be mentioned that such highly strong materials are with a minimal weight compared to steel, and they are also electrically and thermally insulating, which might be a requirement within certain specific conditions. This technology has bright perspectives in the future. Practically, there are unlimited recyclability options, and within the last decade, there was an 8 to 10% increase in the volume of pull Trojan production globally. And seemingly, the automotive sector has discovered this plastic producing technology as well, because now not only straight parts but also curved parts can be manufactured via this process. This is, as you saw, a relatively easy process, but this should not deceive you. A high background knowledge on resin and manufacturing parameters is essential, which is used in order to ensure dimensional accuracy, and this is really problematic on the long run and requires a tremendous amount of experience. And each of the produced parts can be highly expensive. So it's unlike in case of injection molding, the scrap ratio is no joke here. So every single part counts. Every single part might have a tremendous cost that can be attributed to it. And understanding of the aggregated production information and its overall impact on the part quality in general is highly essential. And this is the point where data analytics and AI tools might have an entrance into such production facilities. Within this project, we collected a lot of data, we aggregated them, cleaned them, and try to interpret and interconnect them, and try to use patterns in case of one specific profile, which was the U profile. Within the collected historic data, we had information on 8 different temperature sensors or access to temperature sensor data, also ambient temperature, humidity, speed, pulling force, viscosity information set. Of course, there were the failure modes that are listed in this unfortunately Hungarian code snippet, but as you can see, there were numerous failure modes, and in order to be able to reduce quality-related issues, the failure modes had to be used in order to label the data. Among the data, we had, of course, as always in case of such a problem, many issues. The major problem was that the data were not interconnected. This had to be synchronized, missing values had to be replaced and imputed, and also data cleaning processes had to be implemented. And one major problem was that some of the data was continuous. I mean, time series information, like temperature data that was collected in specific time stamps or times, and of course there were categorical information like the part was OK or not OK, which was assigned to each of the parts, and these informations had to be connected somehow. And of course there were no exact information on the problems that occurred during the production, since the manufacturing company collected data continuously on temperatures and viscosity, for instance, but during the quality control, they just put a stamp on the part that it was okay and not okay, but they did not have data on whether the problem happened on this section or that section, or on this time interval, on that time interval. So you could not connect the physical data to the quality data. So we built up a new database that assigned these problematic issues, and we tried to label the data according to the quality information, and used AI-related classification techniques based on the historic information in order to be able to predict future failures. For this purpose, we use decision tree, random forest, super vector machine, gradient boosting, and logistic regression methods. Unfortunately, it has to be highlighted that the results did not support the initial hypothesis of the company that the temperatures alone that are mainly controlled within this process has the highest impact on the present quality issues that they had. As you can see on these images, we produce relatively low precision recall area under curve values that should have been around 1, but in our trial attempts we had around 0.5. This had many causes, like there was a highly imbalanced data set. Approximately 5% of the data could be labeled with a faulty label, that it had a quality problem, and 95% was technically okay. So we had to apply some kind of minority oversampling technique, but this did not contribute to the informative sense of the data. At this point, we introduced the resin viscosity data into the analysis. That was outside of the initial hypothesis of the company, on the way to reduce quality-related costs. And we also mounted a real-time dimension measurement system. We applied we bought sensors and selected them and applied some interface programming and collected data. Within the project, we had only 3 days to collect dimension informations on the continuously produced parts, and the results can be seen here. You will see standardized values in the following, and you see that we experience some suspicious patterns throughout our investigations that could not be declared with any kind of physical phenomenon that might have happened in the production area. So we, at this point, we decided to introduce further data and metadata on operator-related issues or shift-related information. And we also saw that you cannot find any time-based correlation among the time series. For instance, among ambient temperature, ambient relative humidity, and the analyzed dimensional deviation of the U-shaped plastic part. And of course, there were some experiments performed throughout the production. It has to be highlighted that it is tricky since, as I mentioned, the parts are highly expensive. So the company where the project was carried out was really reluctant to perform any kind of experiment that might purposely harm the product quality. So they just try to make minor deviations in the first place. But in this case, we could convince them to make to implement bigger deviations among the in the production parameters and settings, and let's try to see what might happen. And here you can see in the right that they implemented huge temperature deviation changes. That was more than 3 times of the standard deviation of the usual temperatures, but unfortunately no change in the product quality took place within the investigation of the scenario. And in the middle you see that there were for some kind of reason that could not be declared in the setup, huge temperature alternations. This might, of course, could contribute to sensor problems or to some kind of production issues, but there were no quality-related huge changes in the dimensions that are noted by the red dots. And of course, we try to look for patterns within the temperatures. And as you can see in these figures, they are quite hectic. You see here temperature difference graphs, which can be assigned to each of the quality assurance issues, and you cannot see any kind of pattern. You see extremely different running of the graphs. But if you see on the next 8 graphs, you see that these are quite hectic as well. But these graphs belong to such observation, to such parts that had absolutely no quality issues. So these were the okay parts. These belong to the okay parts, and these ones to the not okay parts. So just out of this simple observation, you might have concluded that temperatures alone did not have the descriptive information that could be enough to somehow reason for the quality problems. So at this point, we introduced some new data, collected some new data out of the production, which was resin viscosity, that had also some interesting aspects and surprises for us. For instance, it was also not known for the company that how huge the scattering, the deviation within the data, viscosity data was, and what kind of impact might it have on the part quality. We also looked for or made some experiments and looked for time evolution of the resin that they used within this pultrusion process, and we saw, as you can see in this image, that with time, on the x-axis you see it in minutes. With time, the viscosity of the resin that was investigated under laboratory conditions had extremely different characteristics. So just the material that they used was extremely different within the production, and it is not easy to see this because you have these resin tanks in bulk. They technically produce their own resin on the site, and it is quite a robust and ugly process, and it is not too easy to see such processes and have them under control. At this point, we saw that we had to refute the hypothesis of the company that just with temperature sensor data we can decrease production-related costs and increase quality of the parts. So we made some kind of, let's say, non-AI related data analytical investigation among the data and metadata that could be collected from the factory, and we collected operator-related data as well on seasonality and season and shift-related alternations, and we found that there are high problems, let's say. So we could find a lot of extra spared resource within the patterns of the working of the company. We saw that within specific times there are much higher scrap ratio. We saw that on different days of the week, for instance, on Saturday, the scrap ratio is much higher than on, for instance, on Monday or Tuesday, and we also found high differences among the operation of the shifts, and with just by investigating this, we could advise the company changes and points where to focus, with which, if I remember correctly, 15 or 20% of quality of cutting in the quality related issues might take place. So this does not say anything about the costs, but on the amount of quality related issues that took place in the production. And of course, based on the dimension measurement system that was mounted within the company, later on statistical process control based investigations could be implemented, which was done as well. And based on such data later on, DOE, so-called design of experiments analysis could be made as well, which unfortunately could not be planned within this project due to the high costs of the scraps. But hopefully in the second phase or the next phase of this project, if it can take place, such experiments can be designed and implemented as well. And of course, there are other tools or ideas in order to attack such a problem. We can investigate time series data in such a scenario, for instance, via cross correlation, which says if the curves shift to the right, in case of a cross correlation setup, then the parameter under study is related to future values of the measured dimension, and on the contrary, if the curves, the cross correlation curves shifts to the left, the parameter under study is related to past values of the measured dimensions. So with cross correlation, we can have a feeling at least that which parameter might influence which one. But of course, this is highly setup dependent, production dependent, part dependent. So this might be used in the future when there will be enough data on dimensional on dimensions in a time series way. And of course, in order to handle time series information, some Granger causality techniques could be used as well in order to make some statistical hypothesis testing to determine whether past values of one time series can be useful in predicting future values on another time series. This might serve with some kind of temporal linkage among the time series information, what we had, for instance, the temperatures, the humidity values, or the pulling forces or speeds, etc. But of course, this won't mean any kind of causality, just this temporal linkage that technically a sense or a feeling whether data might have something in common, or they go together, or they are not related to each other at all. So that was all what I planned to say. And in case you have any question, please feel free to ask. Thank you.
Great, Ferenc, thank you very much. This was really very throughout, deep and very specialized presentation. And if I understood it well, so this is a very good experiment about that machine learning is not only a magic solution in itself. So I would have one question before jumping to the next presentation. So if you could summarize in one sentence, what could be the key takeaway for an SME who is not specialized itself in machine learning, how to handle with this method, how to make one step forward, if you have an advice?
Yes, if I shall summarize such a project, I cannot summarize it in one sentence, but in a few sentences, that for a project where you would like to analyze your data, and based on your data, you would like to make decisions and accept reality that this is my production, I can access it here and there with new ideas, etc. You need to prepare for this. The big disadvantage within the project that I presented to you, that the company did not prepare for such a data analytical project, then they wanted results in a way that I have data. I have a lot of data, I have time series data, I have quality data. Okay, they are not connected in any kind of sense, but okay, we can solve this. We can build up a new database, and according to this database, we will have a lot of structured data. And by using or utilizing structured data and these many modern tools and algorithms, we for sure will find some kind of pattern or interesting anomaly within the production process. Of course, we found anomalies a lot, but not really useful ones for the company. Useful and interesting in an experimental or theoretic sense, but they did not prepare for such a project in a way that okay, let's make a pilot project. Let's select a product and collect data in a way that we consult with a third-party company who is responsible for analyzing and digesting data and making recommendations. And let's see what data might be the most useful, and let's make it in a cooperative way. No, they had their own data. They knew that temperature has the highest influence on the plastic part production, and wanted us to predict future part quality according temperature. And we presented them two different ways. One was this machine learning based alternative, and the second one was the implementation of dimension measurement, that with two independent ways, that no, their hypothesis was wrong, and temperature alone did not have temperature data did not have enough information based on which future quality of the plastic parts within their current setup could be reasoned. And I guess this is the main takeaway, that for such a project you need to prepare yourself. You need to have a pilot. You need to collect data in agreement with some kind of third party, and by cooperating with somebody, not just go for such a project that, hey, I have a lot of historic data and let's see what we can have out of it. By chance, you might have something in it, but it's rarely the case. I guess that's all.
Yes, that was a very good answer. Thank you very much. Thank you for your presentation and the further explanation. And I propose that we can go to the next presentation, and if you will have any questions, we can turn back also to Ferenc. Okay, then Boldizsár, if you can join us and have your presentation, please. Okay. So thank you very much for joining us today, Boldizsár, and I hand you over the speech.
So I would like to share my presentation, hopefully.
Okay, we can see it and we can hear you.
You can see the presentation, not the PowerPoint.
No, the presentation mode is.
Okay, great.
Great, thank you.
So my presentation won't be as professional and detailed as Ferenc's presentation, but I hope it will be enough for you. So today I would like to present our SMCC 400 Industry 4.0 Teaching and Learning Factory for you. But at first, some words about me. My bachelor degree is in computer science. I'm a software engineer, and for my master degree, I did also computer science, but with a digital factory specialization. That's why I'm the one who is responsible for the Industry 4.0 Teaching and Learning Factory. And during my master, I started working at PBM within a dual education program. I started with 3D modeling, augmented reality applications, and since 2021, I'm responsible for coordinating the development and ongoing improvements of the SMCC 400 production line within our company. But I could also develop robot programs and some kind of industrial applications too. So, just a shortcut for the industrial evolution, because with the industry, the first industrial revolution in the 18th century, it's clear for everyone, I think. The steam engines, water wheels, so you know, the machine-based manufacturing comes alive. Exactly, the one device is the spinning jenny, which comes to everyone's mind if we are talking about the first industrial revolution. And the second industrial revolution was in the Industry 2.0 in the 19th, 20th century. It is when the electricity could be afforded by companies, and assembly lines comes in mind. And Ford was the first company who created an assembly line and created the mass production. Meanwhile, in Industry 3.0 is not a kind of revolution, because we also use electricity, assembly lines, mass production, but it's a kind of automated way with computers, PLCs, electronics. This is where automated milling machines, CNC machines, industrial robots came to the industry. And this is, as I said, it's not a kind of revolution. It's just a theoretical time point where the industry developed. As well as the Industry 4.0, it's from 1.0, 2.0, 3.0, and you can see that the 4.0 is a kind of left, the Industry 4.0 is a kind of right, so it's splitting from the 3.0, but the 4.0 is a highly automated autonomous system based on IoT, digitalization, and smart manufacturing. Meanwhile, Industry 5.0 is present from the 2020s, from the beginning, and the European Union found out that humans must be in the factories, in the production, and they try to call humans back to the manufacturing, and this is where the Industry 5.0 came alive with human-machine collaborations, renewable energy, and AI. So the first, second, and fourth industrial revolutions are building for each other, but the 4.0 and 5.0 are a kind of theoretical revolutions, and these are just different kind of mindsets, not a real revolution. About our SMCC 400 system, it's a highly automated smart factory. This is the high-end teaching and learning factory of the company called SMC. It's based on Industry 4.0 technologies. It's a connected and open system. That's why we choose this one, and we have all the source code. We can freely upgrade and modify the machines as we want. It's plug and play, flexible and modular, because we only have the five modules, which is on assembly line. But if we buy another one, we can flexibly connect that module to our already planned system. It has a management software called the Manufacturing Execution System. It's an MES. This software is responsible for the management of the orders, the tracking, how much time did a product spent on each of the modules, or were there any errors within the manufacturing, or who the customer of this product, and so on. And there are some industrial Internet of Things devices like RFID readers or edge machine vision cameras and so on. I would like to share a short video made by us from the training factory, so it will be easier to imagine how it works and how it looks like. I hope you can see it. Okay. Sorry. Let me start again. Yeah, so according to this short video, you could see that the whole system is based on a small RFID pallet, which moves along these 5 modules. This is the 5-module assembly line we have, but it is also possible to have multiple stations. This is a diagram of how the systems could be aligned. And also this 5 station is just a physical order. The logical order could be different from each station. And for example, there is a recycling station, which could be anywhere, which should not be connected directly to the station. You can see we have C405, 402, 405, 406, and 407. And I hope everything is clear now, how the arrows are pointing from which device to which device. And some details about the modules. The C401 is the pallet and container feeding station. The heart of the production is a small blue pallet with an RFID chip. Within the feed, at the start of the manufacturing, feeder feeds this pallet, and an RFID reader reads the RFID chip on the pallet and connects an order number from the manufacturing execution system to it, and this is where the monitoring begins. There are two types of canisters: cylindrical round and quadrangular square canister, and it depends the type of the canister which is put on the pallet depends on the order. If someone orders I don't know, 30 grams of blue and yellow balls pellets within quadrangular container, then a square container will be put on the pallet. Yeah, and the pallet's RFID chip is for identification and traceability. So there are different positions of each module which could be tracked inside the manufacturing execution system. The C402 is the container filling station. So at every station we have an RFID reader which reads the exact pallet and identifies identifies what kind of materials should be used for this product and so on. So the second station fills the containers with solid raw materials. It's three colors: red, blue, and yellow small balls. There could be single, double, or triple kind of colors with different doses. And this station also covers a quality measurement where the filled amount of material is checked. It's a kind of interesting solution because we measure weight with height, because for example, the round containers have an exact circle. This circle is always the same, while the field amount is depends on the order. And if it's filled this way, then we can measure the height of this product, and we can calculate with simple mathematics the volume of the filled balls, and from this we can give a gram value for each product. For example, if we have a 15 gram product, the lower limit is, I don't know, 12 grams. The upper limit is 16 grams, which is the quality is lower and upper limit. And if the field amount is within is out of these limits, then the system turns the product back, and then human have to repair the product, check it on a scale or something, and refill it. But if it's kind of mixed and some really complicated problem occurs, then the whole product could be dropped and deleted, and it have to restart from the first station. The next station is the C405. It's a capping station, so depends on the canister's shape. a corresponding cap is fitted on the container at the station. It's two kind of containers and two kind of caps, cylindrical and quadrangular. We also have a quality control here, but with a machine vision camera. It checks the correct fitting with edge analysis. We had to teach it which is the good placement of the caps and which are the bad within the cylindrical and also the square containers. And meanwhile, a good convolutional neural network with machine vision and so on requires a lot of pictures, more than hundreds or even thousands of pictures to learn what is exactly the good type of cap placing. This machine vision camera only needs 10 or 12 pictures to learn what is the good and what is the not good placement of the caps. The C406 is a container warehouse station which acts as a warehouse for finished or semi-finished products. Finished products are the products with QR codes. You can see that on the right side of the slide. There are some stickers within QR codes in some products, and the semi-finished products do not have these stickers on them. It can store up to 50 containers with their corresponding pallets, exactly. And the warehouse by default allows containers to be introduced, extracted, moved internally according to the needs of the process. Meanwhile, at 2023, we had a collaboration with University of Notre Dame, where students worked with us within in a kind of AI algorithm, where we decided that okay, so now it's Christmas, so the red products are more popular than the blue ones, so the red ones should be placed in a place where the robot arm could easily reach them, because the robotic arm at first, for example, points to right, then the red the containers containing red balls should be placed to the right, and the blue to the top left, because it has to turn around and move there, and it takes a lot of time. And right now for this station it's okay, because it's a few seconds, but for a bigger company with a bigger warehouse, it requires more energy and a lot of time, so this algorithm could be helpful. The final station from the SMCC 400 is the C407. This is the container labeling and dispatching station. This is where these small stickers with the QR codes are placed on this station. And these QR codes contain the exact order number. So with a good application, with a connected application to the system, the products manufacturing lifeline could be tracked, and if there were some errors within the inside the manufacturing, then it could be checked. But if a product is not for dispatching, then the system could turn it around and hand it back to the warehouse station. If the product is made to order, then it is placed on a small ramp which you can see on the picture. You can see the containers with QR codes and the blue caps on a small ramp. The QR codes are also checked with a machine vision camera. This camera reads the QR code if it's readable or not, and also checks if the sticker is placed on the container, where to place it on the container. And if it's not, and it also turns around, and you some human have to interact with the machine and have to repair the machine, repair the product. So the whole system could work fully automated. The manufacturing execution system, the MES, has the capability to create and manage orders. We assign orders to customers, monitor the stocks. We also launch the productions from the MES. As I mentioned, the SMC gave us all the sources of the assembly line, and we created a data visualization application for them. It's called SMCAR application. This is the logo of the application. It's a real-time data visualization software. In augmented reality, we developed it using Unity framework. You can see that on the right of the slide, how it looks like. If you pull your phone into the marker, then you can see some kind of details of the machine. This is this comes handy when you have visitors or someone who you want to present the station, and you do not want to show them some kind of ERP system within secret pages and so on. You just move there, place the phone or tablet or anything on the machine, and it will show you the important information of the machine. We also have a digitalized augmented reality application called Manifest, which could teach you how to use the machine. It's on a HoloLens 2. It's on a HoloLens 2 head-mounted device, and you have to scan a QR code, and the HoloLens knows how you aligned, how the machine is aligned, and you do not have to know anything about the machine. It's a kind of tutorial. It's a kind of guide. You have to press this button. You have to check this, and you can operate the machine without any special knowledge, just wearing this HoloLens 2. This machine is often used in maintenances because it's a big problem if you repair something or maintenance some machine, you skip some step and you forget to check some sensor value, and the machine could could malfunction if if something is wrong. And that's why this exact solution is used within the United States forces, the Hungarian military, here in the Paks, the nuclear power station of Hungary, and in Hungarocontrol within the radar antenna maintenance, because the HoloLens is a kind of hand-free solution. So if you have to climb up to the antenna, you also have this guide with you, but you have 2 free hands and you won't fall off the antenna or somewhere. As I mentioned before, the the system could have a recycling module, but this module was a bit expensive for us, and we decided to build it for ourselves. It's a separate module from the SMC C400, and we begin with a digital twin, a digital simulation of it. So a feeder filled with blue, red, and yellow balls, a gear rotating, and a color sensing sensor, which sorts the balls and recycle the exact balls. At first, it was theoretical. We calculated this, could this work, how fast it could work. Then we created a digital model before we physically ordered and physically placed the module inside our laboratory, and we checked that okay, this could work. Then we ordered it physically, and in the following video you could see that how it works now, because we do not want to leave the digital twin die, so we connected the two systems with a mixed reality glass called Oculus Quest. You can interact with the digital machine, and the same thing happens on the physical machine. It's just a kind of start and stop the machine, or increase or decrease the speed of the machine, or reset the machine state. And this is exactly how the simulation works. So red balls, yellow balls, and blue balls are falling on different parts of this filling station. And this is exactly how now works. I will show you in the video. So you can see that this is the Oculus Quest 2. Quest Pro, sorry. You can see two machines. The closer one is the digital, the other one is the physical. This recycling module is also connected to a solar panel and a battery station. And we also developed an AI solution which checks are there any production in the lines? What kind of materials do the products require? Are there mixed products made? Is there is the sun shining today? Is there any input from the solar panels? And an AI algorithm decides if it's efficient to recycle or not. It's easy. It's a kind of smart solution. It's a kind of AI solution, but it works, and it could also save energy, save time, and creates high efficiency of manufacturing in bigger places, not within this teaching and learning factory, because it's too small, but in a bigger factory, this kind of AI could be really helpful, and it could save a lot of money for the companies. And I think this is a final video of the teaching and learning factory. This is the augmented reality application. This is where I quality check the products. We also connected a collaborative robot to the system, but nowadays it's used for other purposes, and we also use a mobile robot to travel the to take the finished products to the recycling module. Was I a bit quick or not? I hope not. I'm now free to answer any questions you have according to the teaching and learning factory.
Great, Boldizsár. Thank you very much. It was also for me very exciting. I saw it several times, also in real time, and it's fascinating, this whole equipment. So before I have a question, I would also ask the other partners, if you want to ask something our experts, please, then you can go ahead. Yes, Goran, please.
Yes.
Hello to everybody. It's Goran from Preda. Actually, we had the occasion to visit your location of PBN some few months ago, or more or less at the beginning of the year. It was very impressive. It was so impressive that it became one of our pilot activities within the IIS project, Innovation as a Service project. So I would have like a bunch of questions, but I would really like to be short. We want to do this. We want to create some kind of pilot activity on the subject of a learning factory concept, introducing our local vocational schools. So we want to somehow raise their capacities in a way that they could actually apply or try to develop their own learning factory facility in their schools. So my question is whether do you think that this learning factory concept, is it appropriate for vocational school, or is it like a too much complexity? Is it more, I don't know, feasible to do it with the university level, or there is something that we could actually do on the vocational education level?
It's a great question. Actually, we have some high school students, some high school interns, and they also learn to be a PLC programmers or some kind of industrial level programmers, and they could handle the all the PLC stuff, all the I/O links, pneumatics, which are connected to the system. So it's not only for universities, it's for all kind of educations, but I think the minimum level is a high school, is a kind of and it requires some kind of computer knowledge, also some electrical knowledge, but you have to be some kind of technician in order to be able to operate the machine and understand what exactly this machine is. But we also have some engineer visitors from other companies too. And they so we use this machine to present our solutions within inside this small factory, and if we can present them, they often imagine something for their own factory. For example, a data visualization application, or a machine vision application, or something. Yeah. So the teaching and learning factory is a really useful device, and it's always it has a wide range of interested people.
Thank you for the answer. Our intention is to involve the teaching staff from electrotechnical school and from machine school. There are two like most interesting, I mean, most appropriate schools for this type of equipment. Maybe from gymnasium, because they're general working in other wide area. But electrotechnical and machine school for certain. And I just wanted to ask you about the use of this learning factory by the SMEs, but you just provide a little answer that they can also use learning factory in a way that they are testing the solution before they actually invest in some kind of solutions in their.
We could show them some kind of solution which they need on our factory, because if it works here, it will work in the industry.
As I said, I have a lot of questions, but I'm not want to bother you now. I think that we will have the opportunity to actually to cooperate individually on the level of innovation as a service project. So thank you very much.
Okay, you're welcome.
So great, thank you for discussing and asking questions. I have also one theoretical question, if it's okay for you, Borzsár, because you mentioned in the beginning of your presentation that Industry 4.0 and 5.0 are two different directions. And it is very interesting for me, and also maybe for today, it is very actual that it is, so this is very fascinating that all kind of functionality, if I understand well, can be really automatized and made by different applications and mechanic parts. And how can you place the human in it? If you speak about Industry 4.0, for example, if you take that if the future, the children or youngsters have to learn, in which direction should they really learn? How can they place themselves into the life of factory if they will be the future?
So it depends on the factory. Mostly the factories are only on Industry 3.0 level. If a factory is highly automated, it could be called Industry 4.0. For example, near to us in Sharvar, there is a master good factory which will be highly automated. It could be called Industry 4.0 factory. And for Industry 4.0, people mostly needed for maintenance, not to operate the machines, but for maintenance. Meanwhile, Industry 5.0 is closer to Industry 3.0, but in Industry 5.0, the humans' health is also a kind of important point, because with the how should I say that in a beautiful way? So the workplaces should be aligned to be a kind of joy, to kind of fun to work in Industry 5.0, and in Industry 5.0 also the some kind of sensors could be installed to the system, and if someone is not concentrating 100% to the work, or have some health problems, that could be detected, and the man could how should I say that? So if there is any problem with the human resources, then it could be detected easily, and
solution can be provided.
Yes, and the solution could be provided more easily.
Thank you. No, I understand. And I have one last question, only because we are discussing always in our project in SMERF that SMEs need real help in transforming themselves and answering for the future challenges. And if I understand well, so when an SME dealing with production would like to make a step forward, then these teaching and learning factory is really like a very good tool to test everything in. So if an SME steps into AM lab, into the laboratory, you can help them to simulate their processes, if I understand well, and then also optimize them or somehow show how can they adapt it to their own factories. Because I'm not a technician,
some kind of we can implement their solution, but their manufacturing process won't be exactly the same as our factory, but we can parallelize these two assembly lines, a real factory assembly line and teaching and learning factory, and we can have a crossover points where the customer meets and our solutions are meeting.
Great, thank you very much. Thank you very much for both of your presentations, and also thank you for the questions. So I think, however, we indicated that it will last longer. I think I can wait for some questions, of course, but if not, then we can close our meeting or training for today, and we can share with the participants also the presentations and maybe the recording as well. So if you wish, you still have the possibility to make questions. Okay, maybe if you don't have now any idea about this, we are also in the future at your disposal through SMERF project and also PBN and AM Lab. So thank you very much then for joining us, and we wish you a pleasant weekend. Thank you.
Thank you.
Thank you. Bye.